Hi, this is our Chapter 18 lecture on ethers and epoxides and on thiols and sulfides. So the oxygen and sulfur analogs of these types of functional groups. We're going to start with ethers. Our last chapter we had alcohols, where it was just one R group attached to the oxygen along with an H. Ethers have a similar structure, except it's two R groups attached to the O, right? So the shape around the O is the same. It's got that same bent shape. Oxygen has two lone pairs on them, as always. So similar types of molecular geometry, but the chemistry is quite a bit different because that H attached to the oxygen in an alcohol is what was the most important part, really. Here we have no H's on the O, just two R groups. So in general, that's going to make ethers a lot less reactive than alcohols. There are still some interesting things they do, though, so we'll talk about that. We've got a couple of real common examples here. Here's diethyl ether, very commonly used solvent. We used that solvent for the Grignard reaction. Anisole, right? Benzene ring with OCH3 attached to it. We could call it methylphenyl ether, or we could call it methoxybenzene. We'll do nomenclature here in a second. Anisole has a very powerful, fragrant, perfumey kind of smell, so it's used an awful lot in the manufacture of perfumes and cosmetics. Tetrahydrofuran, THF, 5-membered ring, so like cyclopentane but with an oxygen instead of one of the carbons. So an O and then 4 CH2 groups before we get back to the O again. So tetrahydrofuran is another common solvent. It's used just as common, if not maybe even more commonly than diethyl ether is in anionic and Grignard types of reactions. It's called tetrahydrofuran because furan itself has a common name. Furan is the same thing but with 2 double bonds in it, and it's actually aromatic. We saw it before where one of the lone pairs is part of the pi system. So there's furan. It has just one H on each of the carbons because of the double bonds. So tetrahydrofuran has 4 more hydrogens in it. So that's where that name came from. Very, very common name. To name simple ethers, the simplest ethers just have 2 simple hydrocarbon groups attached to them. So if we have specific names for those hydrocarbon groups, we just name them alphabetically with those groups. Okay? So the format is alkyl ether. So 3 words. If I have this compound, for instance, here's a methyl group on one side of the O, here's isopropyl on the other side of the group. It's called isopropyl methyl ether. Over here, this one, ethyl, CH2CH3. Here's a phenyl. So if a benzene ring is attached to the O, that's ethyl phenyl ether. They used that method for anisole up here. They call it methylphenyl ether. So this method only works when we have actual common names for the alkyl groups. But we can, do it with ones that are a little more complicated. Here is CH2 double bond CH on one side, so just a CC double bond on one side, and then benzene with a CH2 on the other side. So this is benzyl vinyl ether. This right here is a vinyl group, VINYL. When I have CH double bond CH2, that's a vinyl group. Whenever something is directly attached to a double bond, that's vinyl. Another common one is allyl. Right? That's CC double bond, then a CH2 and an O. Right? So here's allyl, T-butyl, for instance. Okay, so I think you get that idea. If we have any other functional groups present in the molecule, or if we don't just have a simple name for each of the alkyl groups attached, we have to name an OR group as an alkoxy substituent on the rest of the molecule. So in this one, I have 2 CH3Os opposite each other on the benzene ring. So this is para-dimethoxy benzene. These are methoxy groups here. So those would be methoxy. We could have ethoxy, propoxy. Here's one 6-membered ring with a double bond in it now, and then O-T-butyl. So this is 4-tert-butoxy or 4-T-butoxy. Why? And they call it 1-cyclohexene. I guess I probably would have left that one off if we were considering what we were talking about before, but I guess now is probably a good time to talk about how it is that we decide what actually has precedence when we're numbering the backbone of a molecule here. Let me give you 2 examples that I hope will make it clear. This compound has a double bond and an OH in it. This other compound has a double bond and an OCH3. Well, let's make a little more complicated group there. Let's put a branch to it. Okay. Same double bond. In the alcohol, the primary functional group here is the OH. This name, the name of this compound is going to end in OL. Okay? So the OH is the compound's primary functional group, and that will determine what side the numbering essentially comes on. So I'm going to number whatever side is closer to the OH, even though there's a double bond in there. Okay, so I'm going to call this compound, let's see here, 5 carbons. I'm going to call it 3-pentene, P-N-T-E-N-2-O-L. Because our name ended in ol, O-L, that's what determined where our numbering came from, right? Because I have a double bond and the OH, which someone may have been confused about which one took priority with the numbering. With this one, the ether, the one with more carbons, right? Or I guess the one with the other functional group really is the one that has to be the backbone. In this compound, though, the double bond is the primary functional group because the name of this compound is going to end in -ene. The ether part is going to be a substituent on the rest of the molecule. So in this one, I'm going to number it so that the double bond has numbering priority. So we're going to have an ether group. We're going to have some sort of alkoxy group on carbon 4, and then we'll end it with 2-pentene. So when you have an alkyl group with its own branches here, we start numbering 1 closest to the attachment. So 1, 2, 3. That's going to be a 2-methyl. Right, but the whole thing is attached to carbon 4. So let's start it with 4, then in parentheses, 2-methyl. If that were just a group, we would call it 2-methylpropyl, but it has to be an alkoxy group since it's ether. So 2-methylpropoxy. Okay. 2-pentene. So let me just review with you what we did here. Things like alcohols that have their name at the end of the compound's name, those will take numerical priority, right? Those will help us decide where the numbering goes. Things like ethers or alkyl halides or whatever else is just a substituent on the rest of the molecule. Those will not necessarily have the numbering priority if there's something like an alkene here, which sort of has the last word. Okay? So alcohols have priority over alkenes, but alkenes have priority over ethers, because if we're doing IUPAC naming like this, the ether is just another substituent on the alkene.